Bonjour tout le monde. Hello everyone. Thanks for being here today. Merci de votre participation. My name is Michel Frison and I'm a sales agent for Solaxis Engineers Manufacturing. Today's presentation will be in English, but you may also ask questions in French at the end. La présentation d'aujourd'hui va être en anglais, mais vous pouvez poser des questions en français à la fin du webinaire pour la période des questions. We are very excited to have such a great turnout for our first Solaxis Engineers Manufacturing webinar. This webinar will be the first of a series about 3D printing with thermoplastic material. Slide 2. Today, our aim is to provide you with a status of the industry and where technology is evolving. This first webinar will be very general, but in future webinars will dig deeper into more targeted subjects. We are open to your suggestions for future events in the chat box on the right. Today, our target will be the following: introduction of Solaxis manufacturing, the potential benefits of 3D printing, the state of the 3D printing industry in 2025, how to integrate, optimize 3D printing in your project, and at the end, we'll have a question period. Feel free to write your comments in the chat box and we will look at the question at the end. Next slide. Solaxis Engineers Manufacturing was founded in 2010 and is located in Bromont, Quebec, about 1 hour south of Montreal. Solaxis is a leader in additive manufacturing of thermoplastic with worldwide industrial-grade technologies. Solaxis used the following technologies for 3D printing: FDM from Solaxis, FFF, high resolution SLS. Solaxis is certified AS9100, ISO 9001. We are also Control Goods Canada for our military project and CMMC. Solaxis works with various OEM and Tier 1 in aerospace, medical, industrial, and transportation industry. Solaxis works with leading OEM, Tier 1 and 2 in many countries. For this webinar, we'll leave the chat box open during the event, so you can ask questions that will be answered at the end of the webinar. The microphone will also be open at the end if you want to ask any follow-up question in English or French. The video will be recorded and later posted on our YouTube channel. Now we'll introduce to you our presenter for today, Mario Prévost, who will be leading this webinar. Mario has been with Solaxis since the beginning of this adventure in 2010, and he holds a Bachelor of Engineering from ETS University in Montreal. Mario has been involved in 3D printing since he graduated from ETS in 2010. Now we'll let Mario explain to you the benefits, solutions, and the trends in 3D printing. Take it away, Mario.
Good morning, everyone. Thanks, Michel, for the intro. So today we're going to be talking about 3D printing. Basically, we're going to be tackling some different points about the envelope size, minimum, maximum, the volume, the type of material, lead time, tolerancing, and the benefits that can be brought up with the 3D printing. So to start with, we're going to show you a little bit, a quick overview of our shop floor. You can go to the other page. So that's just a quick image of the type of system that we have. First of all, the FDM from Solaxis. So we have several large format systems that goes from 3 feet by 2 feet by 3 feet envelope. Those types of machines are heated chambers, so they allow us to print parts with high-end material such as Haltem and PEEK, and also other types of a broad range of other materials with the carbon field and other fillers like glass fill also. We can see in the image on the right side the finishing department and a portion of our painting room that we have here at Solaxis. So FDM is a large format heated chamber system that with the accuracy of roughly plus minus 12 thou of an inch, depending on the size of the part and the geometry. they can go with different layer thickness from 5,000 of an inch up to 20,000 of an inch, which allows us to do basically filament 3D printing. At Solaxis, we've also added some FFF, so open source system from different sizes. Some smaller systems, about 10 inches by 10 inches by 10 inches, up to really a larger format that can go that can go up to 1 cubic meter as a size of prints. Those open systems is offering us the capability to use several types of material, mostly in the lower range, so PLA, PETG, which are material that are commonly used in the industry for fit and form and prototypes. But we can also print other complex material that can be carbon filled, glass filled, and flexible material like TPU and TPE. For these types of systems, the smaller ones are quite precise and can achieve some thin wall. But for the larger format, since the machines are up to 1 cubic meter, then we kind of, the tolerancing is a little bit broader, and the layer thickness is also greater. In the larger size and FFF, we also offer the capability of printing with pellets. That system allows to print a really large format part faster with less resolution, but still capable of printing a large volume and a large amount of material in less time. The other technology that Solaxis also offer is the SLS. So SLS is the selective laser sintering. So it's going to be it's a powder-based system, which a laser comes and sinter the powder. The SLS is the SLS that we have here at Solaxis. Allows us to print some part. We've take the decision to go with the PA11 material, so mostly polyamide. And that one, the SLS, one of the main goal of those technology is to go with a higher volume of production, to be able to do a nesting and to have some part that have a better surface finish compared to, let's say, filament printing. So one of the things to consider with the SLS is if the part are designed for like injection, so to have more uniformity in the wall thickness and in the geometry, that's going to bring a better result. Also, the fact that it's a powder that's laser sintered, it allows to get a smaller layer thickness, also more detailed parts. And the SLS basically can be post-treated with a forced vapor deposition system that is capable to seal and smooth the part automatically and brings higher mechanical properties with this type of post-processing. So for some potential benefits of 3D printing thermoplastics, well, generally the Some of the main benefits for using 3D printing would be the cost reduction compared to certain standard processing like molding or machining for a lower volume. Also, it allows us to increase the design to market capability with reducing the delay. One other benefit of the 3D printing is to be able to consolidate part from an assembly. So that way you reduce the amount of components. But at a certain point, there's a maximum of gain. So if you combine too many parts together, then you might have a loss of improvement. So it's just to find the right amount of consolidation that can be brought. The 3D printing also opens the world of design to be able to have some features that were not possible to produce before, or that were difficult to produce with the standard or most commonly used production method before. On the since there's a lot of people that are present here today that are in the aerospace industries, that's just a quick overview of some benefit for the 3D printing in aerospace. So for the design optimization and the weight reduction, we've seen a lot of advantages for our customers. Also, there's no tooling required. So if you have a larger or lower volume of production and you don't have the need to design a tooling to have the tooling produce, the 3D printing is going to bring that to bring the part to your facility quicker compared to other regular production method. So a few of example would be basically galley components, some ductings, some shrouds. We've seen customers that we've built components that were going into the seats for aircrafts, cockpits also, and even tooling. So tooling that's going to help in the industries or your facility to do MRO, so maintenance, repair, and overhaul, that can help to do some assembly in-house or even protect other surrounding components while you're doing certain tasks into the aircraft. For the 3D printing, can give you a quick overview of the state of the 3D printing in North America. So we've seen a growth throughout the years of the 3D printing in the market, and according to different types of evaluation, and we see that there's a potential growth of roughly 22% in North America for the 3D printing market between 2024 and 2030. This growth is basically on all the different technologies that are available. So we see there that there's SLA or stereolithography, FDM, ink printing, polyjet, selective laser sintering. So those are all types of different technologies that exist on the market at this time and that have a different growth because people are more and more using the 3D printing into the industries as they see benefits and they can explore and push further on the limits of the 3D printing to develop parts, develop components, and to increase productivity. With these growth, we see few materials that are coming into the market or that are growing or taking place into the market. To give an idea, the most common material that we can see is polyamide, so nylon. That takes roughly 50% of the market. So the nylon, why is that material so popular? Is because basically it's mostly used in the SLS or MGF for the powder bed fusion printing, and and also it's available on the filament side for FDM and FFF. So they come in various form, either powder, filament, and they can be filled with carbon fiber, carbon nanotubes, and also glass bead. But it can be either from nylon 11, nylon 12, nylon 6. So those are different types of polyamide that have different mechanical properties or different application that can be used also for automotives and other types of industries. The second that comes, it would be photopolymer. So photopolymer is it's the resin that is mostly used for the SLA, so the SLA 3D printing, so stereolithography. This is a kind of a older technology, but that's still broadly used today. So that's mainly why those types of the photopolymer still keeps a big part of the business. And we can see more on the rest. It's of the chart. It's the mostly filament. ABS that is commonly used for entry level prototype fit and form toolings, and the Ultim, which is a polyamide that it's sorry, not polyamide, but a polyether imide, which is a flame retardant material that is commonly used in aerospace and other application that would need a good material that have great mechanical properties, flame retardant capabilities, and that it resists, that maintains its properties with high temperature and low temperature. So on the other slide, we'll see just a quick overview of the different types of 3D printing for thermoplastic. So you can see the filament, liquid, which is all the resin, and the powder. So just to give you a quick overview, we see that there's many players or many companies that developed the system here. So as much as we see different companies that create machines, that kind of broader the range of equipment that are available, and the new players that came in because they developed either new technology or because there's patent that expired. That brings up new development and new add-on to the existing systems. So, for example, some patent that expired for the filament side brought up a lot of company that developed the open source. So from PPU, ABS, even a machine that goes now for higher temperature and high-end material. On the liquid side, there's a lot of system for the vat polymerization, which is kind of the SLA or DLP also. And if you look at systems that have less manufacturers, those are quite are more difficult to access, and that's going to create most of the time higher pricing also, since there's less and less companies that create systems and less systems also that are available on the market. So we're going to see just a quick description, basically, or comparison between the three most commonly used technologies. So we got the FDM or FFF, which is filament-based, the SLA, which is the resin, and the SLS or MGF, which is the powder-based. So basically, on the FDM and FFF side, the key differentiation is the high-temp application for the FDM, and also FFF with the possibility of the size envelope. So they have on the market, there's many types of system that goes from smaller size, so that people that can have almost in their own house, in their living room, for hobbyists, and to the higher level production like we have here at Solaxis for the high temperature. And there's even systems that are available on the market now for really large format. On the SLA, which is the vat polymerization of resin, this technology is going to bring a very smooth surface and excellent resolution for the parts. One of the downside of the SLA is that usually the resin is going to be more affected throughout the time to the UV, so part can be more fragile and brittle. For sure, there's a lot of material that are developing throughout the years, so the property have changed, but that's what we see mostly in the market for the SLA. On the SLS side or the powder side, the NGF, that one is a technology that grew up a lot throughout the year, especially in the past few years. Because of the upcoming of new technology, new techniques. The SLS is going to bring a more kind of a granular surface with high precision or high definition of details, which also going to come with great mechanical properties and isotropic mechanical properties. So it's going to be more uniform in XYZ axis when we do some mechanical testing. Also, the SLS have a great gain for the production of higher volume of parts, since it allows us to do a better nesting, or to nest the part one on top of each other, and to have a more compact processing. So you'll have more parts that can fit in the SLS for the same volume compared to the FDM, let's say. Just a quick overview from some emerging material. Basically, there's two big family. There's the amorphous and semi-crystalline. We won't go too deep in those today. That could be a nice subject to go further on another webinar. But basically, the amorphous is mostly the like standard material that's gonna be that are not going to be changing throughout the time, while the processing and the semi-crystalline are going to be affected more when we do, let's say, the cooling or by the temperature of processing. What we've seen in the in the application and material. There's a lot of new material or new requests that are coming up because of the development that is coming with different manufacturer. So there's a lot of a few popular material and higher demand that we see, especially with tech peak. So high grain material, high temperature resistant, and excellent chemical resistant also. Ultim, which is a big runner for the aerospace application, and also the all the types of industries that need material that's going to be flame retardant. On the reinforced side, there's a lot of material now that we can see coming up with carbon fiber, glass fiber reinforced. Those were usually more higher hand material. Now we can see more entry level material like PLA, PETG, ABS that are coming up, that are being developed to with those types of filler that's going to be helping to increase the mechanical properties. TPU and the TPE, which is a flexible material, are also more and more common. Those materials that can be difficult to print with FDM or SLS, since it tends to warp a little bit more. But those we see a nice market or a nice development and request from our customers to do some sealing joints and to have some part that needs a little bit more flexibility or elongation compared to standard stiffer plastics. And for all of these material, there's a lot of upcoming new requests for ESD, RFI, and EMI. So all application that would be related to anti-static, to even conductivity of material, and to related to electric properties or dissipation for different types of application throughout the markets. So on the other slide, we will see just a quick image to show different application or different market where the 3D printing is used. So we got the aerospace, the defense, electronic for the ESD, EMI, RFI that I was talking a little bit earlier. The consumer product, so end-of-arm toolings, robotic. On the healthcare side, we've seen a lot of emerging application in the past years. So a lot of companies or system now have developed material that is suitable for healthcare and biocompatible. On the industrial and transport side, those are commonly used now for prototype, jigs, tooling, and a use part also. We have a few examples of our image of key application that we've produced throughout the years here at Solaxis. That's really just a quick overview. So we have, let's say, we take the top middle image, the kind of beige or tan part. That's an example of aircraft component that was printed here that we've worked with customers to develop and to do some part consolidation. Though that part was made in Ultim 985. Just beside it on the right, we can see an example of shoe sole for orthotic. Those are commonly printed in SLS. because of the surface finish that is achievable, and also because of the flex and the elongation that we can reach, mostly with PA11 to avoid cracks or breaking, and with the post-processing of the SLS part that can be sealed, that allows the part to be easily cleaned and to avoid the moisture or odor to grow on these types of parts. And one other key market or key application that we've seen with the 3D printing was for the health and safety. So on the lower left side, we see the red part. That part was basically developed with one of our customers to protect electrical connection while they were doing maintenance on the railroad trains. So basically, when the employees were coming in to do some maintenance, they had an issue. They had one accident that an employee got electrified doing the maintenance. So we've developed a custom protective cover. So we've seen that for also lockout, tagout application. That one was made in SLS because we were able to deep dye the part to put forward the color for the security. And we did other application that customer had a specific need for a custom color for their industries. So now we go down to the material and process qualification. So at Solaxis, we're proud to have put forward the process qualification when we with our 3D printing. So that comes from material traceability, robust infrastructure, so the ERP and EPDM, which is the engineering vault and system that are communicating together for our IT. That allows us to track down basically which type of material is going to be used on which production, and to assure that the full follow-up and the full detail that can be provided to our customers. Also, we can provide certificate to assure that the product was made according to the specification. And that's being done, yes, with the IT, but also with the process qualification comes the material testing to ensure that we have the right mechanical properties. So we're going to see on the next page some equipment that we have here at Solaxis, or that can be used also by different manufacturer and different supplier for the material testing. Though, so we see we do the testing of the material to ensure that we have the proper composition. We can find the temperature, heat deformation, glass transition, but one of the key elements is the destructive testing. So for the destructive testing, we put a lot of effort on printing some coupons here and validate if we're able to meet the properties that are on the spec sheet. So traction, flexion, compression. And we've seen that depending of the process and depending of the parameters, those can have a large effect on the results. So what we do some testings, we validate, if we need to modify or to adjust the processing parameters, we do those, and we do other testing to be sure and to validate up to the fact that we are confident that we can be produce part and repeat part that are going to be those the expectation of the customer and the properties that are advertised. So when it comes to adapting the 3D printing in the industries, at the end of the day, there's some key points that need to be kept in mind. So one of those would be, the first one and the most important one is to define one potential project. So if you're new to the 3D printing world and you want to try something, you want to try the 3D printing, first of all, define the project, find a medium to complex part. If it's a part if it's a new part, does it need to be redesigned? If it's prototype, tooling, end of use part. After that, you need to validate the needs. So what's the main goal that you're looking to reach? What do you want to achieve with with your part? So if it goes to rate reduction, cost reduction, part consolidation, which I've mentioned a little bit earlier, it's a little bit more complex for the consolidation because you need to find the right amount of part that you want to put together, and sometimes it's going to need a little bit of redesign to maximize the 3D printing gain, or to to use properly the 3D printing and not simply combining part together that come from another process before. After that, it's really important to verify what would be the technical requirement. So if you need, if you have specific needs for mechanical properties, chemical resistant, different types of finish, the aspect of the part that you want to have, what's going to be the environment? Is there going to be vibration? Is there going to be impacts? Those are all points that are super important to consider, as you'll need to, it's going to affect the type of material that's going to be selected, and that's going to be doing like, that's going to be just ensuring that your project is going to be a success. We've seen with some of our customers that had also put together internal standard, and process specification. So especially for the aerospace market or industry, a lot of companies have put together some standard in-house to qualify and to assure that the parts are produced accordingly, and that they are going to be repeated throughout the time, even if it's different production year after years. On that side, if you don't have any standard in-house, that's important to indicate on your drawings the need or the goal that you're trying to reach. If you have like specific mechanical properties, if you have to specify also the orientation of the part to be printed, so that way you can ensure that the part is going to be produced the same way time after time, because orientation during the build process can have an impact, or will have an impact, depending on the type of technology that is selected, and also on the surface of the finish, of the surface that you'll be receiving for your parts. So once those are kind of clarified, then you can provide a 3D file that can be on most of the format commonly used, so either SolidWorks, CATIA, STEP, IGES, and STL. When it comes to STL, it's really important to provide a high definition of STL to avoid any surface defect and to ensure that all the details going to be there. Also, what we've seen for STL is that sometimes we lose the scaling. So if you provide an STL, please ensure to just put some basic information about the volume or the size of the part if you don't have any 2D drawings that come with it. And lastly, but not to be lastly, basically on the engineering side and the support, Solaxis can offer some coaching, some design validation at some point to help you with the optimization for additive manufacturing. So we've developed tips and tricks throughout the years with our knowledge base, with multiple projects that we've made for customers and throughout our learning curves. So we would be more than happy to help you with your request and yeah, to give some tips. We don't do full design, but we still try to help and to coach our customers because the main goal of our business is to ensure that you have a project that's going to be a success at the end of the day. So that's going to be bringing up to the Q&A section. So if someone has any question, please feel free. If not, we have some question that we've just brought up.
All right. Thank you, Mario. It was very interesting. I mean, this technology is evolving every year, every day, every month. There's new stuff coming out, which is very interesting. We have a first question here from Monsieur Bret.
I think you're muted.
Yeah.
Yeah, I was double mute. Sorry about that.
No
Salut Michel. Salut Michel. Thank you for the presentation. Very interesting indeed. You mentioned a couple of things about process qualification and mechanical properties. It's always been with this process the challenge for us to have some guaranteed mechanical properties to make our analysis when we design a part. So where are we now? I know that NCAMP is working on developing some industry standard for process qualification and material qualification. Are you following that, or are you using your own internal process specification when you mentioned qualification? That would be a first question. And also maybe, are you strictly doing build to print, or you are also doing some design and build for aerospace industry?
Yeah, so that's a good question. So we have qualified some machine as per the NCAMP series of tests. So some dog bones or coupons for pull test, flexural test, mostly for Alton 985 for the aerospace application. But we are doing also different types of validation with our machine. So either temperature validation and other pull tests. I'll be really honest. We didn't do all the testing for all the material that we have because we have roughly about 110, I think, different types of material. So the most common one was the Alton 985, but we still do a few coupons for the other material to validate the mechanical properties. As for the So that comes from few details for the mechanical and the also the process qualification for the machine to ensure that the machine is going to be repeatable with coupons that are made at different position into the print. So that way we can assure that the machine is going to be repeatable if we print a part on the left corner or on the right corner, in the front and the back, especially with the FDM.
All right. There was also another question if we were following the advancement in the in some of a group.
Yeah. Sorry, we were talking about the. For the design. For the design, it's mostly built to print. To be honest, we don't do design for qualification. We still work with our customers. We have customers in the aerospace that we did some coaching with them, but we don't have any like FAA or Transport Canada delegate here at Solaxis. But for defense and defense, military, industrial customers, we did some complex design with them, and we did some work around to provide them some tips to design parts that are being produced here at Solaxis.
Very good.
Thank you.
All right. I have a question for you, Mario. I mean, we haven't shown it, but I mean, on the productivity side, I mean, there's possibility of nesting parts, right? So you can print, and I was surprised to see that when I visited the operation the first time. We can do nesting of multiple small parts in one big printed bundle. Maybe you can elaborate on that. How many parts you could print, like of the smaller size, and then nest into one big assembly.
I don't know, Mary, if you want to go to the slide 21, the key application. Okay, so there's two ways to nest. So depending on the technology and the FDM or FFF for the filament, we can see an example of nesting on the right side. So on the FDM or filament side, to do the nesting, we put parts side by side, so one beside each other, up to the full envelope that can be 1 meter by 1 meter or 3 feet by 2 feet, depending if it's higher temp or lower temp application. On the SLS side, because of the technology, because of the processing, then yes, we can nest many parts one on top of each other because there's no support material. So what is supporting the part or filling the gap between them is the powder that is deposited between the part that are not. The powder that is not centered, that's what's going to be holding the part. So you can put, let's say, a hollow part and put a part inside it, and you can put all those parts on top of each other. So depending on the format or the size of those parts, we did some build that had 1,000 parts. We did some build that had 400 parts, 200 parts, and one full build takes roughly only 1 day to print. Compared to let's say FDM that can have longer build time. So we have some parts that are currently in production that takes more than 160 hours.
Ah oui, j'ai fait un webinaire là, on a l'impression 3D, mais c'est pas grave.
All right. So there's really potential for of doing productivity and generate production parts for production, not only prototypes. And I think that's one of the main things that I saw is now the industry is evolving toward more production. It's taking over, and the machines are more performant. You can nest, you can do many things to produce volume of parts that you couldn't do before, which is interesting for customer who have a need for big projects or have needs for lots of parts, right? At a good cost and a short lead time. So that's something interesting. All right. Maybe we go back to the questions, Marie. Vivienne. Okay, so basically, Mario, a customer can come to us with a concept, an existing part, or drawing a 3D model, a catch-up file, a step, and then we can work with them to help them develop and find alternatives to their parts, right? I mean, we're AS9100, so we can do aerospace parts, we can do automotive. I think one of the points that I find very interesting is some of the parts have very complex geometry internal, like we can do boxes or exhaust or ducting with internal, very complex geometry. Is this something that you see more and more with complex parts with intricate geometries that are that can be done at a good cost with 3D printing?
Yeah, well, that's one thing that we've seen, and that comes also with that's one of the big benefits of 3D printing is the freedom of design, because we're adding material and we're not removing material compared to a standard machining process. The fact that there's also many new companies that are providing machines and systems, that brings up that people are now buying 3D printers for their own application, so in-house application, and also for the business, but smaller. Most of the time, it's going to be smaller system, and that's going to push the design even further. So people now are designing more and more complex parts, and they are pushing the limit to do some intricate geometry, intricate infill. We've seen customers in the robotic industries for end-of-arm tooling now that we are doing grippers that have channel inside to do some vacuum, to do the vacuum and to allow parts to be used on the robotic grippers. We have some application where we can do some scaffolding or some void inside the part, so that way we can reduce the weight and have some robust part and good mechanical properties while reducing the amount of material that is put into place.
Very good. So full traceability of material with your ERP system, testing. So we really can deliver a complete part and reduce the part count, which is very interesting because if you have 2 or 3 parts that you can combine into one printed element, it's cost reduction for everyone.
Yeah, okay. When it comes to the combining of the parts, like I said, sometimes we need to do a little bit further evaluation. So it's not just gluing all those parts together without modifying the geometry. If you put a bracket beside another one, you might want also, you're going to be, you might want to modify a little bit the design to merge the walls together to reduce the thickness and not just adding the part one on top of each other.
Okay, very good. Any other question? Any points that maybe someone wants to clarify? S'il y a des questions en français aussi, aucun problème. Oui, allez-y.
Bonjour, mon nom est Hamdi Selmi, puis je travaille pour CVTech de Romontville. J'ai une question un peu générale, mais peut-être j'obtiens des réponses. En fait, c'est par rapport à des matériaux, mettons, sur mesure. Nous, la problématique qu'on fait, ou bien le départ du sujet, c'est qu'on veut tester parfois des pièces, la résistance mécanique des pièces avec différents 3D. Donc, on travaille sur l'amélioration du 3D et on garde le même matériau. Puis nos matériaux qu'on utilise, c'est des matériaux injectés plastiques avec des fibres de carbone parfois ou du verre. Mais est-ce qu'on parle parfois des recettes un peu spécifiques pour se comparer ou bien pour avoir des propriétés mécaniques proches de notre matériau de base?
On a différents matériaux disponibles, donc on a quand même plusieurs matériaux. Le fait d'avoir des systèmes ouverts nous permet un petit peu plus de latitude à ce niveau-là. Donc oui, on a des matériaux qui sont chargés de fibres de carbone, fibres de verre, certains même chargés de céramique.
Parfait.
Mais il faut vraiment prendre le temps de comparer les propriétés mécaniques. On a même certains projets avec des clients vraiment spécifiques dans lesquels on travaille pour le développement de filaments. Mais ça, c'est vraiment, il faut avoir une étude de cas qui est assez robuste et un assez grand volume. Mais sinon, si vous avez des applications de votre côté, vous cherchez vraiment à rencontrer les propriétés, n'hésitez pas. On a de l'information sur notre site web pour certains matériaux, mais il y en a quand même beaucoup en termes de développement, en cours de développement. Donc, l'idéal, c'est vraiment de nous poser la question. Ça se peut qu'on ne les ait pas affichés encore, mais qu'on soit en train de les travailler.
Excellent.
Ouais, et aussi, on a des bonnes relations aussi avec les fournisseurs de matériaux, donc il y a toujours moyen de travailler aussi avec nos partenaires, les fabricants, les manufacturiers des matériaux pour supporter les clients. Okay,
merci.
Merci beaucoup pour votre question, très appréciée. OK, d'autres questions? Comme j'ai dit tantôt, la présentation et la vidéo vont être uploadées sur YouTube. Donc, si vous voulez la partager avec vos collègues, the presentation will be uploaded to YouTube. So if you want to read it again, see it again, don't hesitate. Our contacts are here. We can do prototypes. We can do volume of parts, 10, 50, 500. I mean, we're open to work with everybody, and we have a lot of expertise. So thank you so much, everybody who's been here today. We look forward to work with you guys on future projects.
Also, just to add up on that, Michelle, thank you a lot for being there today. If you have any subject that you would like to us to treat on another webinar, please feel free to let us know. We'll put together a list of the requests, and we'll try to generate other webinars for a specific or more specific and precise subject.
Parfait. Merci beaucoup, Mario. Merci beaucoup, tout le monde. Et passez une belle journée.
Merci, bonne fin de journée.
Bonne journée.
Thank you so much. Bye-bye.